This first section explains the one move that the Drude theory makes. Take a working theory built for one substrate and bolt it onto another, where its premises are flatly false, then keep it for what it predicts, not for being true. Drude does exactly this. It takes the kinetic theory of a dilute neutral gas and transplants it onto the electron sea of a metal, whose density runs roughly 1,000 times higher and whose charges interact strongly. Every precondition is violated 1,000 times higher and whose charges interact strongly. Electrons become the gas molecules. The ion cores become the scattering walls. The whole chapter is one move, a deliberately naive substrate. Swap. It is kept because its successes seed intuition, and its failures, sharp and specific, draw the map that the quantum theory of solids will later have to complete. This part explains the single move that turns Drude's classical metal into Sommerfeld's. One substitution rescues Drude. You keep the entire classical electron gas, the same dynamics, the same collisions, the same conductivity machinery, and you swap only the velocity distribution. Maxwell, Boltzmann goes out, Fermi-Dirac comes in. Pauli exclusion is the whole content of that swap. Everything else Drude built survives untouched. The consequence that carries the chapter is a scale. At metallic densities, the Fermi temperature runs from about 10,000 to 100,000 Kelvin, so room temperature is effectively zero. The electron gas is degenerate. It is cold, nearly frozen, with only the thin sliver near the Fermi surface free to respond. That single fact dissolves Drude's catastrophe, the missing specific heat. The electrons were never classically hot, so they never carried the 3/2 K each that no experiment could find. The chapter is that graft and its reach. This section explains why the chapter on the failures of the free electron model is a fault localization path rather than a defect list. Every failure the free electron model produces gets re-indexed onto exactly one of 3 idealizations. Those failures are the field-dependent Hall coefficients, the wrong sign thermopower, the unexplained resistivity temperature curve, and the cubic specific heat term. The 3 idealizations they map onto are these: ignoring the ions field, ignoring the ions field, ignoring the ions field, ignoring electron interaction, and ignoring collision detail. The partition itself is the payload. Symptoms sorted by which simplification generates them become a repair order. The verdict lands on the first assumption, the neglected ionic potential. It causes nearly everything, and the cure is to treat the ions not as scatterers, but as a static periodic lattice. So a catalog of anomalies becomes a program. Bind each failure to its idealization, then fix the idealization. This section explains what a crystal's order really is, and why the object that captures it is a symmetry group rather than a list of atoms. A crystal's order is fully captured by asking from which points it looks identical in both arrangement and orientation. The Bravais lattice is that set, the discrete translations that leave the pattern invariant, the 3-dimensional integer lattice acting homogeneously on space. Define it by the symmetry, not by the contents. An object is what it does. Everything that later solid-state physics needs, diffraction in electron bands, is fixed by this one group before any atom is named. The honeycomb sharpens the boundary. Every vertex sees the same neighbors, yet alternate vertices see them rotated by 180 degrees, so orientation fails. The honeycomb is therefore no Bravais lattice at all. It is a 2-point basis sitting on a sparser lattice. Content is decoration. Periodicity alone is the object. This section explains the reciprocal lattice, the single structural idea. The chapter turns on. A crystal repeats. Therefore, every function that lives on it repeats too, and the natural way to describe a repeating function is by the plane waves that share its period. Those special wave vectors are ordered rather than scattered. They themselves form a lattice, the reciprocal lattice, the Fourier dual of the crystalline space. That is the whole chapter in one line. Real space periodicity corresponds to a discrete lattice of allowed wave vectors. Fix the direct lattice and this dual is forced uniquely. Everything the book builds next, the Bragg peaks, the Brillouin zones, the Bloch electrons, is one question asked of this single object. Which wave vectors K respect the crystal's translations? Once you hold the duality, you can predict each of those instances yourself, rather than memorize them. This section explains how X-ray diffraction reads out a crystal's structure. A diffraction pattern is the reciprocal lattice made visible. That is the whole chapter in one stroke. Fire. X-rays, with a wavelength near 1 angstrom, the interatomic scale, at a periodic array of ions, and sharp peaks appear only where every scatterer interferes constructively. The condition, worked out two ways, collapses to a single demand. The change in the scattering wave vector, capital K, defined as K prime minus K, must itself be a reciprocal K, defined as K prime minus K, must itself be a reciprocal lattice vex constructively. Bragg reads this as mirror planes, where the path difference is twice d times the sine of theta, set equal to n times lambda. Von Laue reads it as a Fourier condition that e to the I, capital K, dotted with capital R equals 1 over all lattice sites. These are the same statement in two dialects. Chapter 5, Built Reciprocal Space. This is where the experiment photographs it. This section explains how Chapter 7 classifies the ways a crystal maps onto itself. Chapter 4 gave the lattice only its translations. Chapter 7 asks what else carries the lattice into itself. Rotations, reflections, inversions. The discovery is that these do not float free. The lemma that makes the argument go through, from Ashcroft and Merman, is that every rigid symmetry factors as a translation, call it the translation by a lattice vector R, composed with an operation that pins one lattice point. Figure 7.1 shows the case. A 90-degree rotation about a pointless axis is just a lattice shift, times a rotation about a pointless axis is just a lattice shift, times a rotation about a lattice point. So the full space group splits cleanly into two parts, the translation subgroup and the finite point group that fixes the origin. Classify by that point group residue, and the infinite lattice collapses to a finite verdict, 7 crystal systems, 14 Bravais lattices. The chapter is the factorization that makes counting possible. This section explains what a repeating potential does before you name any particular one. A potential that repeats on a lattice hands you a symmetry, and every symmetry launders itself into a conserved label. The lattice translation operators commute with the Hamiltonian, so their simultaneous eigenstates all wear one quantum number, the crystal momentum number. Bloch's theorem is nothing more than diagonalizing the translation group before the Hamiltonian. Once you do that, the eigenstate is forced into a single shape, a plane wave, e to the I k dot r, multiplied by a function u that repeats with the lattice. The whole payload of the chapter is what symmetry alone fixes before any particular potential is named. The crystal momentum K is confined to a Brillouin zone, the levels split into bands, one energy function epsilon sub n of K for each band index n, and the free electrons come back as a limiting case, recovered when U goes to a constant. This is the same move as Neuweather. Invariance under a group buys you the labels that its irreducible representations wear. This section explains where band gaps come from in the merely free electron picture. A weak lattice potential is almost a lie the electron can ignore everywhere except where it cannot. Take the free electron plane waves and switch on a small potential U. Generically, two nearby levels merely repel each other by an amount of order U squared, a negligible nudge. But where two free electron energies coincide, precisely the Bragg planes, where the magnitude of K equals the magnitude of K minus K, the nudge becomes a splitting of order U, and a gap tears open. That is the entire chapter. Band structure is degenerate. Perturbation theory keyed to symmetry. The potential does nothing until degeneracy hands it something to lift. So you can already predict where every gap lives. You read it off the geometry of Bragg reflection, not the strength of U. This part explains the tight binding method and how it meets the free electron picture from the other side. A crystal is two opposite fictions converging on the same object. Chapter 9. Started from free electrons faintly disturbed by the lattice. This chapter starts from isolated atoms whose orbitals just barely touch. The generative move is this. Take a bound atomic level, replicate it at every site, and form the one-block symmetric superposition the lattice permits, the sum over all lattice vectors r of e to the ik dot r times the atomic orbital phi evaluated at r minus r. With zero overlap, the band is flat, energy pinned at the atomic level. Let neighboring orbitals overlap, and that degeneracy spreads into a band whose width is the overlap itself. So a band is what a localized state becomes under lattice symmetry. The same block skeleton carries both limits. This is the reconciliation of the two pictures, not two rival ones. This section explains why the chapter needs so many methods for calculating band structure. The reason is a single wave function pulled between two irreconcilable regimes, and every method here is a device to bridge them. A valence electron must oscillate violently inside each ion core. Orthogonality to the tightly bound core states forces this, and equivalently, its kinetic energy there is enormous. Yet the same electron must run smooth and plane, wave-like in the interstitial region between the ions. Each of the two earlier approaches fails on one side of this split. Chapter 9's nearly free electrons choke on the core oscillations because they demand far too many short wavelength plane waves. Chapter 10's tight binding cannot reach the smooth interstitial. The cellular method, APW, KKR, OPW, and the pseudopotential all accept the same split of space into atomic core spheres and a smooth interstitial, and then each picks a basis that honors both. Grasp that dichotomy, and you can predict each method's trade-off before you meet it. This section explains the semi-classical model of electron dynamics, and its whole move is a single substitution. Keep Newton, swap the dispersion. The free electron law survives intact into a periodic crystal. That law has two parts. The time derivative of position equals h bar times k over m, and h bar times the gradient of x bar ln sub n with respect to k with minus e times the quantity e plus v cross h. Both survive, provided you make one replacement. You replace the free energy, h bar squared times k squared over 2m, by the actual band structure, epsilon sub n of k, and you read velocity off its gradient, velocity equals 1 over h bar times the gradient. Every effect of the lattice potential is compressed into that one function. the response to external fields stays classical, and the band index n is conserved, so the electron never leaves its band. The chapter's role in the arc is exactly this compression. Quantum mechanics enters once, through epsilon sub n of k, and then the dynamics runs by hand. From the curvature of epsilon sub n alone, you can predict the adjacent cases, holes, effective mass, and the sign of the Hall coefficient. This section explains the semi-classical theory of conduction in metals, and its whole move is to use quantum mechanics for exactly one job. Keep quantum mechanics for one task only, computing the band, the energy epsilon sub n, as a function of crystal momentum k. Then let the electron move as a classical wave packet whose Hamiltonian is that band. That is the whole chapter. Position and crystal momentum evolve by Hamilton's equations. The velocity equals 1 over h bar times the gradient, with respect to k of the band energy epsilon sub n, and h bar times the time rate of change of k equals minus E times the quantity electric field, E plus velocity crossed with magnetic field, E plus velocity. The vacuum parabola h bar squared k squared over 2m is demoted to merely one possible band shape among many, and every free electron embarrassment, the wrong sign, Hall coefficients, the insulators, the holes, dissolves once the shape of the occupied band, through its curvature and its gaps, dictates the response. Effective mass is just what the second derivative of the band energy, the tensor of curvatures, does to Newton's law. This section explains how the Fermi surface becomes measurable, how an instrument reads its hidden shape off a magnetic field. Everything before this built the Fermi surface as an abstraction. This chapter turns it into something an instrument reads off directly. Here is the move. Immerse the electrons in a magnetic field, and their motion perpendicular to it quantizes into Landau tubes. Sweeping the field slides those tubes through the surface, one at a time. Every property tied to the density of levels then oscillates strictly periodically in 1 over h. That includes the magnetization through the de Haas-Van Alphen effect, along with the conductivity and the magnetostriction. Onsager's relation fixes that period as a single extremal cross-sectional area of the surface, taken normal to the field. A hidden geometry leaks out as a periodicity in a tunable knob. Rotate the field, harvest every extremal cut, and reconstruct the shape. This section explains how the Fermi surface of every metal comes from a single recipe applied to the free electron sphere. One recipe generates the whole zoo of metallic Fermi surfaces. Take the free electron sphere size to the valence, fold it back into the reduced zones, then let the weak periodic potential round every corner the sphere meets at a Bragg plane, and pinch off the thinnest necks. Valence alone sets the difficulty. The monovalent alkalis keep their sphere inside a single zone, reducing to Sommerfeld's free electron gas, confirmed to parts per thousand. Trivalent aluminium spills across 3 zones, and its fragments reconnect into Hall tubes that fix the sign of its Hall coefficient. The chapter looks like a periodic table catalog. Its actual content is that one distortion map, run outward from valence and checked against a Haas-Van Alphen data at every metal. This section explains why the relaxation time approximation fails, and what replaces it. The relaxation time approximation is a lie of convenience. It fixes the collision rate as a constant clock, indifferent to the very distribution it relaxes. This chapter's move is to make the rate a functional of the state. because Pauli exclusion permits scattering only into empty levels. Both the rate at which an electron collides and the spread of electrons emerging from a collision depend on the occupancy G itself. So 1 over tau of K is not a postulated constant, but something constructed from a microscopic scattering probability, W sub K K prime, and a Lieb distribution from a microscopic scat K prime, and the Lieb distribution permits algebraic relaxation gives way to a self-consistent integral balance of in-scattering and out-scattering. The collision operator now reads the state it acts on. This section explains why the theory of one electron energy bands works, even though it rests on a fiction. The whole edifice of one electron bands rests on a fiction, and this chapter confesses it, then explains why the fiction works. The exact object, n electrons Coulomb coupled to all the others, is insoluble. Every escape here repeats one move, fold the interaction back into a renormalized single particle problem. Hawtree averages the rest into a self-consistent field. Hartree. Fock adds the anti-symmetry term, exchange. Screening softens the bare one over R into something short-ranged and local. Landau's Fermi liquid names the fixed point. The real excitations are dressed quasi-particles in one-to-one correspondence with free electrons. The adiabatic correspondence is the payoff. It explains why counting non-interacting levels described metals so absurdly well. This section explains why removing a single electron from a metal forces the surface back into a calculation the whole book had been allowed to ignore. Remove one electron, and the infinite crystal idealization sends its bill. The work function splits into two pieces. It equals minus the Fermi energy plus a surface term. The first piece is the bulk term, the Fermi energy, unchanged from the endless solid. The second piece is the surface term, the double layer, a dipole sheet where the surface term, the double layer, a dipole sheet where the surface cells carry a charge that the bulk's inversion plus cubic symmetry had forbidden. That is the chapter's single move against the whole book. Every prior chapter zeroed the surface because only one atom in 10 to the 8th power lives there. Yet the long-range Coulomb potential makes that thin layer's dipole drop finite and orientation dependent and so irreducible. So one metal shows different work functions on different crystal faces. That asymmetry is the seed of contact potentials, of thermionic and photoelectric emission, of every phenomenon where an electron must cross the boundary out. This section explains why two ways of classifying the same solids can disagree, and why this chapter's classification cuts where the previous one could not. Two classifications of the same objects need not agree, because each indexes a different invariant. Chapter 7. Sorted crystals by symmetry, pure geometry, and so it is blind to whether a solid conducts, since every crystal system holds metals and insulators alike. This chapter re-indexes by where the valence electrons sit, and the payoff is a physical cut the geometric one cannot see. The sharp divide, metal versus insulator, is rigorous only in K-space, a partially filled band, or none at all. Real space electron distribution gives no such keen knife. It yields only soft, prototype, anchored subspecies of insulator, covalent, ionic, molecular, metallic, and hydrogen bonded. Here is the move that makes the whole chapter go through. The crisp axis lives in the Fourier dual of the intuitive one. This section explains what cohesive energy is and why every bonding type reduces to one structure. Bind a crystal, then ask what it costs to pull it back apart into free atoms. That energy per particle is the cohesion, and it equals the depth of one well. Every bonding type the chapter surveys, van der Waals noble gases, Madelung's summed ionic salts, covalent and metallic, reduces to the same variational skeleton. A long-range attraction, the term that changes by type, fights a universal steep short-range repulsion from electron overlap. The equilibrium lattice constant sits exactly where their sum bottoms outerlap. The magnitudes fan across 2 orders of magnitude, about 0.02 electron volts per atom for solid argon, several electron volts for sodium chloride, but the structure is invariant. Cohesion is a minimized total energy. The chemistry only sets the attractive law. This section catalogs the phenomena that a static lattice, every ion frozen at its Bravais lattice site, cannot produce at all. Freeze every ion at its site, and a whole class of phenomena becomes not merely mispredicted, but strictly zero. Here is the catalog of exactly those: lattice-specific heat, thermal expansion, melting, the temperature-dependent part of metallic resistivity, thermal conduction in insulators, sound, phonon-limited transport, superconductivity. The static lattice is a 0th order truncation. Its failures are precisely the observables that live in the motion it threw away. The generative move is this: to locate where any model breaks, ask what vanishes identically under its central assumption. The absent observable is the diagnostic. Ionic dynamics is the entire content of everything listed here, not a correction bolted onto the equilibrium theory. This part explains why one small assumption gives you the entire dynamics of a harmonic crystal. Displacement small compared to the lattice spacing, that single wager buys everything. Expand the crystal's potential energy in the ionic displacements U of R about the equilibrium, Bravais sites. The constant term is just the cohesive energy. The linear term vanishes because equilibrium is a minimum, and U truncate at the quadratic term. A solid becomes what its Hessian says it is. 3 n masses coupled by springs, a bath of independent harmonic oscillators once you diagonalize. This is the ordinary critical point move. First derivative dead, second derivative rules applied to about 10 to the 23rd coordinates at once. Everything downstream is bookkeeping on that one quadratic form: the normal modes, the specific heat, the continuum limit into elasticity. Where the excursions stop being small, as in solid helium, the whole scheme collapses and you start over. This section explains why the quantum theory of the harmonic crystal exists at all, and what single move fixes the classical failure. Classical harmonic crystals predict a constant specific heat, the Dulong and Petit result. Every real solid violates it as the temperature approaches 0, the heat capacity dying like T cub-dar omega times h bar o omega. A crystal is one move. A crystal is 3n, coupled oscillators, but diagonalized into normal modes it becomes 3n. An independent ones and an independent ones it becomes 3n. In Penix solves exactly with energies n plus 1/2 times h bar omega. So each mode's excitation count n becomes a countable quantum, the phonon. The ionic displacement field quantises into sound, quanta exactly as the electromagnetic field quantises into photons. Specific heat then falls because modes whose h bar omega is greater than kBt cannot be excited. They freeze out. Quantization is the temperature dependence. This section explains how the phonon dispersion relation is measured. The setup is simple. You point a beam at the crystal, you measure what energy and momentum the beam leaves with, and the phonon dispersion, omega as a function of the wave vector k, falls straight out of 2 bookkeeping equations. The first equation is energy conservation. It ties the neutron's change in energy to the phonons it emits, minus the phonons it absorbs. The second is crystal momentum conservation. It ties the neutron's change in momentum to the wave vectors of those phonons. This is the same. No other move you already hold. A symmetry begets a conserved charge. Here the symmetry is only the discrete one, shift by a Bravais lattice vector, so the charge is conserved only modulo, a reciprocal lattice vector. Two equations, two unknowns, the wave vector k and the frequency omega. You read the spectrum directly off these equations rather than computing it from a model. Whether the probe is a neutron or a photon changes nothing structural. It changes only the probe's energy momentum relation, its E of p. That is why the analysis splits cleanly into a probe, blind core, and a one-line substitution. This part explains why anharmonic effects in crystals are the whole story, not a footnote to the harmonic picture. A harmonic crystal is a lattice of independent springs. Diagonalize it and the phonons come out exact, eternal, and non-interacting, which means a purely harmonic solid never expands when heated and conducts heat infinitely well, since nothing scatters a phonon. Both of those consequences are absurd. The absurdity is where the physics lives. It sits entirely in the terms that the Taylor expansion throws away past the quadratic order. Nonlinearity is what lets the modes talk to each other. So anharmonicity is not a small correction sitting on top of the harmonic answers. It is the sole author of a whole class of phenomena that harmonic theory predicts to be either zero or infinite. Here is the generative move. Linearizing decouples. Whatever a linear theory sends off to a degenerate limit, either zero or infinite, is exactly what the next term in the expansion restores. This section explains why phonons exist in metals at all, and what dissolves the gap that would otherwise forbid them. Left alone, a metal's ions form a charged plasma. Their bare Coulomb repulsion is so long-range that it forbids the acoustic branch entirely, locking every long wavelength mode at a single ionic plasma frequency, written omega p. That is a gap. But neutron scattering and the specific Heats T-cubed term both demand the opposite, they demand the opposite, they demand the opposite, they demand that the frequency omega grow linearly with the wave vector k. The conduction. Electrons dissolve the gap. This is the same screening move as Chapter 17. You divide the bare interaction by the dielectric constant epsilon of k, whose Thomas Fermi behavior has a pole going as 1 over k squared at long wavelength. That pole exactly cancels the ion plasmon's own 1 over k squared, and what is left is omega equal to c times k, a genuine acoustic branch. So the dress sound speed c is roughly the square root of m over capital M times the Fermi velocity vf. This is the Bohm-Staver relation, and it puts the phonian speed at about 100th of the Fermi velocity. Screening is what makes a metal's charge lattice sing acoustically at all. This section explains how an insulator's entire electrical behavior reduces to a single function, and how that number is built from the atomic scale. With no free charge to short it out, the field simply enters the material, and the whole electrical life of an insulator collapses to one function, the dielectric constant, epsilon, as a function of frequency omega. The chapter has one job: to manufacture that macroscopic number from the microscopic polarizability of the ions. The gap it must close is this. The field actually felt by an ion is not the macroscopic average field. The surrounding polarized medium adds a contribution of its own, so the ion sits in a stronger field than the bulk average suggests. The quantity that bridges the two scales is the local field, and the bridge relation is Clausius and Mossati, which writes the macroscopic epsilon in terms of a per-ion polarizability alpha. Everything downstream is one consequence of that same map: refraction, the rest-Strahlen band, and the splitting of the ionic modes. The case that reveals the structure most sharply is ferroelectrics. There, the local field feedback runs away, epsilon diverges, and the polarization sustains itself with no applied field at all. This section explains why a semiconductor is metal physics with the carrier count set free. In an ordinary metal, conductivity is a fixed density times mobility. In a semiconductor, the density itself is thermal. The electrons are lifted across the gap, so the carrier count is exponentially sensitive to the gap width and to temperature. The generative move is this. The two bands sit nearly empty and nearly full, so their carriers form a dilute, non-degenerate gas, the Boltzmann tail of Fermi-Dirac statistics. That one approximation buys the law of mass action. The product of the electron and hole densities, n times p, depends only on temperature and gap width, never on doping. Impurities do not touch that product. They slide the chemical potential, trading electrons for holes while n times p stays fixed. Every doped case follows from this single invariant, and the chapter before the junction is where it bends. This section explains what happens when a semiconductor is doped unevenly across space. Dope a single crystal with a spatial gradient. Acceptors on one side, donors on the other, and equilibrium imposes exactly one constraint. The electrochemical potential is flat everywhere. It cannot bend, so the bands must. Carriers drain out of the transition region until the built-in electrostatic potential precisely offsets the doping-driven density difference, the doping-driven density difference. Here is the generative pattern. Inhomogeneous. Semiconductor physics is just the homogeneous carrier statistics of chapter 28, plus the demand that mu stay constant across the crystal. Bend the material, and the bands bend to hold mu flat. Rectification is that same asymmetry answering an applied bias, predictable before you compute it. This section explains why the perfect crystal the whole book has built is a fiction, and where the real physics lives instead. That flawless, periodic lattice is a thermodynamic impossibility above absolute zero. Almost every property you actually measure lives in where the periodicity breaks, not in the periodicity itself. The perfection is the idealization, the defect is the observable. Here is the move that forces it. Minimize the free energy of a lattice missing n ions. The formation cost grows linearly in n, one fixed energy penalty per missing ion. But the configurational entropy, the number of ways to choose where to put those vacancies, grows faster than linearly for small n. So the minus ts term always wins near zero, and equilibrium drives the vacancy count away from zero. The equilibrium number works out to n times e to the power of minus epsilon over kBt, where epsilon is the formation energy of one vacancy, kBt is the thermal energy, and n is the number of sites. It is exponentially small at low temperature, but it is never zero. That single argument generates the whole chapter. The ideal crystal explains cohesion and the band structure. But ionic conductivity is carried entirely by vacancies, and mechanical weakness comes entirely from dislocations. So the quantity you measure is always defect, mediated. Perfection is inert. It produces nothing you can observe, and entropy makes it unreachable in any case. This section explains how one chapter treats diamagnetism and paramagnetism as a single piece of bookkeeping. Every magnetic response the chapter names is one operator applied to different microscopic energies. Magnetization is the field gradient of the free energy. In symbols, the magnetization is the whole thesis. Single differentiation is the whole thesis. All the volume times the partial derivative of the free energy, F, with respect to the field H. Susceptibility is its second derivative. The susceptibility, chi, equals -1 over the volume, times the second partial derivative of the free energy with respect to the field. The sign of the curvature partitions the phenomena. Energy that rises with the field gives diamagnetism, where the susceptibility is less than 0, closed shells resisting flux, the Larmor response. Energy that falls with the field gives paramagnetism, where the susceptibility is greater than 0, moments aligning, the Curie response. Diamagnetism and paramagnetism are two signs of one piece of bookkeeping. Ashcroft and Merman's move is to fix that thermodynamic scaffold first, so every later case, atomic shells, free ions, conduction electrons, is simply a matter of which energy you differentiate. This section explains why the interaction that orders spins in a ferromagnet is not really magnetic at all. Call the interaction magnetic, and you have already misread it. The moment-to-moment coupling that aligns spins in a ferromagnet is electrostatic, ordinary Coulomb repulsion wearing spins clothes. The dipole fields are 1,000-fold too weak. The ferromagnetic transition sits at hundreds of Kelvin, not the few Kelvin that dipoles could enforce. Spin enters only through the Pauli principle, which chains spin symmetry to spatial symmetry, and spatial symmetry carries a Coulomb price. So the energy depends on relative spin direction, even though no spin term appears, a Coulomb price even though no spin term appears in the Hamiltonian. The hydrogen molecule singlet to triplet splitting is the whole mechanism in miniature, and it demands abandoning independent electrons. Exchange lives in the correlations that band theory throws away.